right, it looks like we have some more folks joining in with us here. Welcome to the session and good morning, everyone. Thank you for being here. I'd like to introduce one of your first speakers of today. Paul Gauvreau is the CEO and founder of BlockPoint Systems. And Paul, whenever you're ready, you can go ahead and begin your presentation.
Awesome. Thank you for the introduction, Molly. Hi, everyone. My name is Paul, and I am the CEO and founder of BlockPoint. And today I'm going to be going over how an immutable database can benefit your data-driven application. So I guess we'll just jump right into it. So the first thing is I'm just going to give you a quick overview of some of these slides that we're going to run through. First, I'm going to touch, what is immutability and what are its benefits to your application. Then I'm going to go over what I think are some of the 3 biggest problems in data-driven applications and how immutability can help solve them. Then I'll give you a little introduction to BlockPoint, what we do and what is MDB. And then we're going to go over multi-version data and multi-version data being a naturally event-sourced means of tracking changes and what that means. And then we'll jump into a use case. So I guess, let's jump right in there. So the first thing is immutability, right? So what is it? What does immutability mean? And what does having immutable data mean for your application, right? So immutability is a fancy word for your data can't be changed, right? And that provides 3 key advantages that we're going to go over. The first advantage is security. So if your data can't be changed, it can't be altered, it can't be modified, it increases the security of your system, right? You're able to grab a record in your database and you're able to mathematically prove and verify that that record is what it was when it was put in there, was put in there by the user that entered the data, and check and just mitigate a lot of risk associated with storing data. Now, the next thing is auditable trails. In order to achieve, immutable data and achieve this inside a database, right, you can't delete anything. You can only store different updates or differentials and amend new data. And all these historical values that you start to store in the system build a very clear auditable trail of your data, who touched it, what they changed those records to, and how those values have changed over time. So it makes it great for kind of compliance and regulatory reasons as far as having visibility into your application and how your application is storing the data and how people are viewing that data. And then the third key benefit of immutability is analytics, right? So as I started to mention, in order to kind of maintain the immutability in a database, you have to store all these historical values. And in doing so, you provide yourself with insight into the entire audit trail of the database, right? So you can jump back in time, look at previous versions of a record, and then analyze how that has changed over time. So what I'm going to do now is I'm going to overview what I think are 3 of some of the biggest problems in modern applications today. And then we'll kind of give you a little overview of BlockPoint. And we'll talk about, how immutability can help solve these problems, right? So the first problem is ransomware. And I'm sure you guys, right, are all familiar with this or have at least seen it on the news recently. But ransomware has spiked in the last year as things have kind of moved more digital and is a massive problem, right? And with databases sitting behind almost all applications, they're a big target for ransomware attacks, whether it be to encrypt the database, to modify data in there, or to steal the data. They're a big kind of potential point of failure in the system that can bring down your whole application, right? And so, a couple quick stats are: as the average company pays, almost $250,000 on ransom. They can be down for, on average, 19 days. And then 1 in 3,000 emails contains malware. So we're going to talk a little bit about how immutable databases are poised to kind of help prevent ransomware and fix a lot of the problems there. Then the next thing is dark data. Dark data is data that's collected that is not used. So whether that be unstructured data that you can't analyze, or it's you've got multiple databases in your data warehouse and you can't join between those data, so you're losing valuable insight into how that data relates to one another. And then the third problem that we'll kind of go into is non-holistic data sets, right? So traditional databases only store data at a current point in time. And so this kind of gives you limited data, right? Generates limited statistics. So we're going to talk about how when you're storing all these historical values, you get a more holistic view of what your data looks like, how it changes over time, how users are interacting with your system, and what you can do to gain value out of that data. So before we go into those, I'm going to tell you a little bit about BlockPoint. So BlockPoint, we built and designed a database called MDB, and MDB uses a interfacing language called BSQL. BSQL stands for Blockchain Structured Query Language, and we chose to make MDB SQL compatible because SQL is, it makes it highly adoptable, right? The SQL language is very familiar to a lot of developers. Structured languages, help abstract a lot of the complexity associated with, adding immutability to your application, doing analytics, querying the data away from the developer. And it makes it easier to integrate, right? So BlockPoint is main kind of service is this MDB, which stands for Multi-Version Database Management System. So what I'm going to do is kind of give you a little overlay of, so here are the three kind of problems that we mentioned, or here are the three kind of key value adds of immutability that we mentioned on the slides before. And I'm going to kind of put them in relation to our immutable database and what we do to utilize these advantages and kind of solve some of these issues, right? So the first one being security, right? And that's ransomware, data breaches, hacks. So because MDB is a fully immutable system and it stores all historical values, we have a bunch of commands, and one command is check validity. And these commands allow you to go into the database and validate and identify data breaches, right? So you can validate that your data hasn't changed. And in the case in which your database has been breached or your system's been compromised, you can identify the location of that data breach, and then pull up logs and start to analyze, okay, how did this data breach happen? Where did this come from? And what was the problem, right? And so this is a big deal because in traditional databases, right, there's no good way to analyze data breaches. And this check validity command is pretty low on performance implications, and you can just set it to run in off hours every day, every week, whenever you kind of deem fit. And then the next thing is auditable trails, right? So in order to maintain the immutability of the system and to not modify old records, MDB and the BSQL interfacing language don't support update and delete commands. Instead of using update and delete like you would in traditional SQL databases, we have two commands called amend and discontinue. Now the change in language is just to illustrate that these commands aren't physically modifying data on disk, but instead are kind of appending new information to the system that's updating maybe the state, right? So while traditional databases are written in pen, when we work with this immutable system, MDB is written in, or when traditional systems are written in pencil, MDB is written in pen because it can't be changed and you can kind of prove those values. And then the last thing is analytics, right? Because we're storing all these historical values, BSQL has a bunch of time travel capabilities that allow you to jump back in time and effectively, interact with the database as if you were looking at a snapshot. And so this becomes really powerful as you start to do, lifetime analytics and run temporal queries and try to gain more value of the data from that perspective. Right. So I guess back to this real quick is that one of the key focuses that we had was how do we build, a more secure, a more modern database without losing a lot of the performance that you get in a traditional relational database management system. And so we consider MDB to be a blockchain-based database, right? In the fact in which everything's immutable, there's a very clear ledger-like log, but the system's still relational. You can still do queries. You still get the same kind of transaction speeds and stuff like that. So the first thing we're going to look at is preventing ransomware, right? So on the slides previously, one of the big problems, right, with modern applications is the threat that ransomware poses on your application, right? And if you think about a database, like what is its main function? Its main purpose is to, protect and store your data. And so if your data is not immutable, right, it's like, how is it protecting it? So there's two key things that MDB and BSQL do. So one is that the BSQL language doesn't have those update and delete commands, right? It's got amend and discontinue. And so that prevents, from a basic standpoint, people from using the interface to modify or change data. And then beyond that, since it's an append only system, the files are actually locked and permissioned by the OS to be write once, read many, right? They're append only files. And so that means in order for, ransomware to come in and to encrypt over your database or to kind of modify data, it would need to get root permission to your system, and it'd need to kind of break those OS permissions, right? So this adds a lot of great security benefits with kind of no added development out of the box. Now, the next thing we're going to talk about is analytics, right? So it's now that you are storing all this additional data, you're storing the historical records of it, you have a more kind of holistic view on your data, right? You can go in, you can mathematically prove the record's integrity to make sure that that data hasn't changed, that the person that inserted it was who they say they were. But that data is still structured, right? It's still relational. You don't lose what makes a relational database. And so in addition to that, you can have all these new types of queries. So one of the commands kind of we'll go over, one of the keywords is a lifetime keyword, right? So if you think a traditional kind of select statement, BSQL has this lifetime keyword, and the lifetime keyword essentially allows you to peer back into the history of the system and look at different versions of the database. And so this kind of comes into, data as a strategic asset, right? So traditional databases, right, changes, if you want to track changes in the system, you've got two options. You can build system version tables, or you can take snapshots, right? And both add a lot of overhead to the system and have limitations as far as how granular they can be. If you're tracking changes daily and you're doing snapshots every day, in a system in which you've got a lot of updates or, a lot of modifications, you're going to lose a lot of that accuracy of the changes of your data. But then in a case in which you're doing system versioning tables, you could have an update command that really propagates into 4 or 5 different commands by, updating other tables and slowly propagating that new version of the record throughout the system, right? So there's a lot of problems with this. But, in MDB, right, the BlockPoint way is because everything's, built in and it's an append only, right, database, and it's a multi-version system, all changes are tracked. So accessing previous versions of the system is as simple as, setting your transaction time or adding this lifetime keyword to a select statement and looking at, when a record was deleted, when it was modified, what the previous version was. And so that kind of brings us to like traditional kind of snapshot implementations. And, in traditional systems, right, running a snapshot, you have to, run it during off hours. So you can't run them very frequently. It adds a lot of overhead as far as disk space. And then if you run out of disk space, those snapshots can get deleted, right? So if it was a very valuable snapshot or you're looking at what you want to change, you could lose it. And the next thing is you don't always know what you want to snapshot in your data. So here's a basic illustration of, snapshotting in traditional databases, right? So these X's kind of mark records that have changed. And then the snapshot is a replica of the page that just stores their previous value. So you'll see you get a lot of dead space and kind of redundant use in this overhead that can cause performance problems. So how do we do this in MDB, right? What's the BlockPoint way? And if you look here, we've got this base file, and when things are updated to the data, it's just appended, right? So everything's built off this kind of append only system. And so that makes sure that, data is never lost, and previous versions don't affect, database performance, right? So it reduces system overhead, it reduces redundant data, and it also kind of builds in analytics from the start, right? So here's kind of a basic illustration, right? Is that, traditional databases, your snapshot is at a fixed point in time, so it's not going to be as granular. But in our database, in an immutable kind of multi-version database, you've got all the records. It's instead of your snapshot being time-based, right? It's mutation-based, because you can really look at when something changed, what it changed to, and its entire history. So with that being said, the next thing we're going to go over is just a basic use case. One of the companies that we work with is Willport, and what Willport is doing is they are building a digital trust, right? So if you think, grandma's will, and in that will, grandma wants to make sure that everything that she stores is very secure, that there's clear audit trails, and then Willport wants to know that if they're digitalizing, right, this traditionally pen and paper process, that they secure themselves, and they mitigate a lot of risk associated with storing that data electronically. And so that's kind of where an immutable database comes in. That's where we come in, is we mitigate a lot of the risk associated with storing this very sensitive information, but then also provide clear audit trails and analytics into the application itself. And so that's the, I guess, a quick, overview of, how immutable databases, can be used to kind of further solidify and kind of solve a lot of problems with data-driven applications. A little overview on BlockPoint ourselves. We're always looking to, work with more developers, more people. So, we're happy to send out registration codes, and we'd love for you guys to kind of sign up for any developer instances. We've got a bunch of documentations online that explore, the B-SQL language, how to integrate it into applications, how to connect it to like different ETL pipelines and set up data warehouse providers. And then, we'd be happy to set up a demo if anyone's interested. But as far as that goes, here's my email, and we'd be happy to kind of answer any questions. I don't know if anyone has anything in the chat. Yeah, so one question is, could you talk a little bit more about previous versions of the database do not affect performance of the existing database state? Yeah, so inside the database, we store a lot of system metadata files and indexes that track the state of the system. So if you wanted to query something from the current state and time, you're essentially going to be looking at an index, and that index is going to pull up the current version. And the database itself, there's a bunch of different optimizations that we allow you to enable in your schema that define how that data is going to be used in different storage and access patterns. And by understanding, the rate at which you're going to update a record, the rate at which you're going to insert query and kind of interact with that specific table or that specific schema, we kind of change the metadata that we store behind the scenes to allow you to get the highest performance, right? Because as you could imagine, since nothing's ever deleted, every time you're updating, inserting, or deleting data, your database is just going to grow. It's going to get larger. And it's really going to kind of build out more information as to kind of what's happened in the past and what's currently in there. So right, to access the current state, our optimizer will kind of access different system metadata that tracks, what the state of the database is. And then that also kind of falls true with accessing previous versions of the database. When you kind of do a snapshot or you're querying over the current state of the database joined with, maybe a previous version of the database, the way that kind of these lifetime indexes are set up it allows you to kind of get the same performance. Okay, so now we have another question from David. So I may have missed it, but how do you deal with schema changes? Yeah, so there's a couple different ways that you can do schema changes in the system. And there's a couple limitations, as you could imagine, because since data is immutable, you can't delete stuff. So there's two main options, right? You're either adding a record, right? Or you're changing the data type of a column in a record, right? So you're adding a new column, or you're changing the data type of an existing column. Those are possible, right? Because you can go in and essentially what you do is you'd create a new table and you'd migrate the data over. And we have processes for doing that inside the system, so you preserve the timestamps in which all that data was modified. In order to drop a column, you would have to kind of manually create a new table, remove the column and port the values over. And then just disconnect that old table in the system. So as you can imagine, right, because things are immutable, it makes it harder and it's a little less forgiving in some ways to actually, modify your schema once it's been created. So you're kind of restricted to creating a new table and moving it over if you're removing data from the schema itself. So another question is, does using this type of system affect the way people want to run transactions against it? Maybe it is better to do 10 crude operations all at the same time instead of one operation every minute. Okay, so there's a couple interesting things that come to this. So one feature of the database is it's completely lockless. Because everything is multi-version, right? Because we're storing all these historical records, we use an optimistic concurrency control protocol behind the scenes. And what that means is that you don't run into the traditional bottlenecks you do when running concurrent transactions in a kind of three-phase locking environment that most systems use. So as far as concurrency controls go, you can run much more highly concurrent environments in our database and get better performance than you would in a traditional system. Now, in order to kind of preserve the immutability of the system while also allowing you to have the same commit and rollback features of a transaction that is known to traditional databases, until you commit your data, that data is not considered to be immutable, right? So you're going to insert that data, and if you roll back that transaction, those are actually stored in special kind of staging files. And then once you commit that transaction, we have cryptographic metadata that's stored with those files is verified, and then that's archived down to those append only files that we had kind of talked about earlier. And then, so now Pedro asked, do you have a proprietary database management system or support well-known databases? Okay, so this BlockPoint built its own database from the ground up. And we built that from scratch, and it's built using Golang, and it can be run in parallel with traditional systems like Oracle or SQL Server, or it can be run as a replacement. We've got almost all the same kind of features and functionalities, and then we've got a massive doc site that goes over the different commands you can do. The language itself, BSQL, was modeled after T-SQL, right, which is Transact SQL from SQL Server. So it's going to look very similar to that if you guys are kind of familiar with the different systems. But other than that, I mean, if there's any other questions, I'm happy to answer them as well. Kind of we'll be in the booth answering questions as well. And then all our docs and everything's available online, so I can kind of type up the doc site. Yeah, so there's Cassidy just sent the docs. So that links to the BSQL documentation site, and so that shows you how to create a blockchain. So blockchains in our system are synonymous to tables, and you'll kind of see that full syntax layout of how you actually use the commands. There's examples in there. And then under the tab, you'll see a bunch of other stuff. So we have all the same kind of traditional identity access management, roles, kind of permissioning that you can do record level encryption that you'd expect to see in, Postgres or Oracle or SQL Server. But the underlying, technology, the main difference is that the append only files and kind of the immutability tracking that we do is built in. So you don't have to do that. So how much overhead will this technology add to scalability options? So are there any kind of scalability options in particular that kind of come to mind, Pedro, that you would want me to focus on? I guess from a general standpoint, so since we built the system from the ground up, we were able to remove a lot of overheads with, locking, being able to, update data. And in doing so, we've got a lot of optimizations that make certain things faster, right? So if you're inserting data, it can be, on a factor of 10 times faster to insert that data into our system, opposed to doing it in, like a SQL Server or Oracle system. Like in many situations, a highly tuned, enterprise database, it'd be good if you got at like 12 milliseconds, in kind of financial setting. In our system, you can cut that down into like microseconds. So, 200 microseconds, stuff like that. But yeah, and then Cassie just sent our dev link right there. And then we'll also kind of be in the booth if you guys have any more questions. Here's my email, so feel free to drop that. But other than that, thanks for joining. And yeah, I guess unpredictable storage growth. So yeah, so Pedro, so storage is cheap now. It's much cheaper than it used to be back in, the early 2000s. And data can be kind of one of your most valuable assets. And so one of the things like we like to say is like when you look at your application and you look at, every update and delete command you have in there, you really kind of need to perform a cost benefit analysis as to, okay, why am I deleting this data? Why am I updating it? And if you can't answer that question, it's hard to answer the question of, okay, what is this data going to tell me about my users 5 years from now, or 2 years from now, or a year from now? And so storage isn't the problem that it used to be as far as cost wise. So it's everybody's moving towards this store everything and analyze and use that data later, because once you delete it, it's gone. But once you have it, if you could always vacuum and clean the system down the road if you deem it as not worthwhile. But anyways, yeah, thanks guys for joining and tuning in. I think this is about to cut us off, but yeah, feel free to stop by the booth.